Hello everybody, Jordan Girth here from the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 180. Glad to have today's presenter, Dr. Stephen Goodman, Senior Program Advisor to NOAA and NASA for GeoXO. The title of his presentation is Lightning Variability and Change, Perspectives on El Niño, La Niña, and Beyond. I'm glad to have our facilitator, Dr. Adrian Lopez-Lago, meteorologist from National Weather Service Weather Forecast Office in Louisville, Kentucky. As you just heard, this session is being recorded. There will be an opportunity, as always, for Q&A after the presentation. I would encourage all attendees to post their questions in the chat, and we'll field them in the order they are asked. We're particularly interested in questions and discussion from our field offices and regional headquarters. Also, if you have signed in with a generic office account and you're asking a question in the chat, please note your full name so that we can get in contact with you following this session if necessary. We're always looking for future presenters. Please contact our Tower S team, Kashad Bowman and Emily Maddox, if you would like to present. And if you're looking for training materials, Ross Van Til can answer all your questions on that. I'd like to thank our Tower S team. We are here in a conference room this week. We have our all-hands meeting, so we have a few members of our team there on the camera. But I'm particularly thankful for Kashad Bowman and Emily Maddox, the Office of the Chief Learning Officer, the GOES-R JPSS program, our presenter, facilitator, and all of you for being with us today. Without further ado, let me give Steve a little bit deeper introduction. He, as I mentioned, is the Senior Program Advisor to NOAA and NASA for the Next Generation Geostationary Extended Observations Program follow-on to the GOES Weather Satellite Series. He's also an affiliated professor at the University of Alabama, Huntsville, and has authored more than 80 peer-reviewed papers on high-impact weather, lightning, precipitation, and climate variability during his 40-year career. Dr. Goodman previously served as the Chief Scientist for NOAA's GOES-R program and as a member of the NOAA-NASA Space-Based Lightning Mapper instrument teams. He retired in 2017 from NOAA as the Senior Scientist and member of the NOAA Council of Fellows. With that, we'll turn it over to you, Steve, for today's Satellite Book Club presentation.
Thank you, Jordan. Can you all hear me okay?
Yes, we can. Thank you.
Okay, perfect. Okay, so I'm going to talk about a topic. We don't hear too much about climate at the book club. I've really enjoyed them. I think it's a great thing you guys are doing. This topic here on lightning variability and change is a version of what we've been doing the last few years with the bulletin of the AMS. They have a special supplement on the state of the climate, and this upcoming August will be the third year that we've made a contribution, and I'd like to show you some of the results and then a couple of figures we're going to have in this year's issue addressing lightning variability and change. We had a session at the AMS in Baltimore, the 37th conference on climate variability and change, and I borrowed some of the title words here from that session, which was talking about El Niño, La Niña, climate variability and such and beyond. So hopefully that's not a problem. I figure many of you might have gone to the satellite sessions and may have missed the presentation, but I'm going to give an update as well, so this should be useful to you. All right, my co-authors are part of a WMO project that we're all working on for the Global Climate Observing System, where lightning was added as an essential climate variable back in 2016. And so we've been addressing how do we gather up all the data sets, some of which are commercial data sets of lightning, and make these available to the scientific community. All right, so I'll give some motivation for why do we care about lightning with respect to climate. I could argue that it's the most common natural hazard on Earth with hundreds of millions of lightning flashes per year worldwide. And the interest in extreme weather, public safety, resilience of the energy grid, fire ignition, insurance loss, natural source of nitrous oxide, which also is a essential climate variable, And the total economic cost in a year is on the order of about $6 billion, I think is a good number. We're trying to develop climate data records for lightning. And one thing that's not been done other than for our satellite program is a good description of the metadata details on the performance of the observing system. So for example, these ground-based lightning networks, which a lot of you have access to, other than what they publish in the literature, you don't have a good description, and we're trying to gather that from them for this project. And they've all agreed to do that, and I'll say more about that as we go through here. But things like what is the detection efficiency, false alarms, and you can read about the GLM, the lightning mapper from NOAA. The performance is documented in the operations website. We also want harmonization of the space-based and ground-based lightning data because they do offer complementary information. And this special note here that no single system is 100% detection efficiency effective. They all have their limitations. And so the integrated observing system, which I'm a big fan of, brings a lot of these data sets together so we can have as complete data description as we might possibly get. Now, the WMO is very interested in what I'm calling grand challenge science questions. So the interest is not just lightning in a vacuum by itself, but how is lightning related to the other essential climate variables, such as severe storms, fires, aerosols, clouds, precipitation. And I'll show you a few slides at the end about what we're seeing with respect to a warming Arctic. So what's the value proposition for lightning and climate? As I said, lightning is now an essential climate variable as declared by the WMO and GCOS. And ECV is a physical, chemical, or biological variable or group of linked variables that contributes to characterization of the Earth's climate. The data sets provide the empirical evidence needed to understand and predict the evolution of climate, to guide mitigation and adaptation measures, assess risks, enable attribution of climate events to underlying causes, and underpin climate services. And everyone here I know is aware that Dr. Spinrad and NOAA are very much on board with climate and climate change and understanding what we can and the benefits of that. The work we do is required to support the work of the United Nations Framework Convention on Climate Change and also the Intergovernmental Panel on Climate Change. And I show a couple covers here of some reports that we've been involved with. We did a report after our initial meeting in College Park in 2017 when the team was formed on lightning for climate. And some of the big issues back then were, well, we mostly have these commercial data sets besides GLM at the time. And how do we advocate and influence the commercial data providers that they should provide their data for the greater public benefit? And because we had the overarching umbrella of the WMO, they didn't view this project as being parochial in any particular nature. And so the major total lightning or global lightning networks that operate at low frequency, such as the Worldwide Lightning Location Network, Vaisala's Global Lightning Dataset 360, and Earth Network's Total Lightning Network, they're all on board. They're all providing their data at no cost. And we're going to build a landing page where people will be able to get to these data sets. So weather impacts on society and what are the societal benefits of lightning? I gave you some examples here in picture form of phenomenon that do have lightning: tornadoes, hurricanes, floods, forest fires, volcanic eruptions, blizzards. Everyone's heard Jim Cantori get all excited about thunder snow. With regards to hurricanes, we're interested in the research that suggests that there's a benefit of including lightning as one of the predictors for rapid intensification. For tornadoes, even especially non-supercell tornadoes, where it's not clear what the storm is going to do, there is a signature that the lightning produces, what we call the lightning jump, that indicates a rapidly increasing trend of lightning, total lightning, that occurs before the tornado as the updraft's intensifying. For floods, I think the largest interest is in the Intermountain West, where the radars are beam blocked by radar. And so having the lightning data as an augmented data set is important. You can read the list here on the right of some of the societal benefits. And one of the things that's gaining more traction now is NWP. And the folks at the Global Systems Lab in NOAA, their new mesoscale model or regional model called Rufus is going to include a lightning forecast. It's being done experimentally now with the rapid refresh, but it will continue, and we hope to improve that kind of capability going forward. Here's the space-based component of the Global Observing System. This is from the WMO space program. So how are we doing in filling out the geo ring for lightning? So we have GOES 16 and 18. Hopefully we'll hear soon when GOES 19, GOES U will be launched. That will replace GOES 16 in the GOES East position. The latest instruments have fixed a few problems and issues that occurred in the first two GLM instruments, but they were already assembled and mounted to the satellite, and we couldn't do anything to remove artifacts such as spray light, which is greatly reduced in GOES 18 and GOES U, and some electronics issues. The Chinese on the right here, FY4A, the Fenyang 4A satellite, has a lightning mapping imager, and it was launched in December of 2016. We launched GOES 16 in November of 2016. It still operates. It has a limited field of view of mainland China and, excuse me, I got a Microsoft notice. Mainland China, and then in the wintertime, Northern Hemisphere, they rotate the view to see Australia. And their next generation Fenyang 4 C, D, E, and F, or whatever they're going to have, will also have lightning imagers. At least that's the plan in the WMO observing system database called OSCAR. And they will have an expanded field of view. And then lastly, Europe, Meteosat third generation, the first imaging satellite, I-1, has a lightning imager. It's not the same as the GLM instrument, but it's very similar. It looks at the same spectral lines as the GLM does. It has a little higher spatial resolution at nadir, but when you're looking at most of Europe, the spatial resolution is pretty much the same as GLM in looking at lightning. And they're still in commissioning. We can't wait to see their data. Okay, so we have data requirements for the lightning climatology that we're doing for the essential climate variable. We're interested in the lightning stroke density. So that would be like, for you familiar with the GLM, that'd be like GLM groups, which are like strokes from the ground-based network. We want consistent harmonized data, global density grid at 10 by 10 kilometers, or about 0.1 by 0.1 degrees. Right now, we're planning to put out monthly for all these data sets. Some will be daily, some will be hourly, like Thunder Hour, which I'll say a little more about. By making a Thunder Hour data product, you eliminate or maybe hide some of the problems of the performance of these different systems, which have receivers located non-uniformly around the world. So our space-based optical data, which is my primary interest, we have the NASA Tropical Rain Measuring Mission, the International Space Station Lightning Imaging Sensor. That mission just ended in mid-November. It had been going on for 28 years. NOAA and NASA have put together the geostationary lightning mapper, of which we have 4. GeoXO, the next generation, will hopefully also have 4 lightning mappers with improved performance. I'll say a little bit to wrap up at the end. I mentioned China, I mentioned EUMETSAT, and then the commercial ground-based data sets. And I mentioned regional networks here, which would be like the National Lightning Detection Network, would be of interest because the European Center for Medium Range Forecasting, when the plan was put together, said, you know, we'd like to know if the lightning is in cloud or cloud to ground, and the regional ground-based radio frequency networks do the best job of that. And so we'll also have the National Lightning Network, and we'll have some of the European networks who are willing to contribute their data. And on the right, I show you lightning flash density from the lightning imaging sensor, showing you spring of 2020, 3-year difference, and then GLM on the bottom, where you see the lightning density anomalies as well compared to previous years. When I get to this later, pay attention on the anomaly in the lower right. You notice in the sort of central part of the US and Central America, you see that the anomaly is negative. In the Sierra Madre, it's positive, and then you see some positive anomalies down there in the Gulf of Mexico. All right, the Global Climate Observing System has an atmospheric observations panel on climate. They have a 5-year implementation plan, and the topics that we wrote up for that are lightning, thunder days, and ionospheric potential. GUAN is the highly calibrated global sounding network that is used as reference data sets. And one of the projects going on is to measure ionospheric potential on a couple of those sounding balloons and get a better grip on that. And then state of the climate in 2022, this is the BAM supplement. So we're also doing 2023, and the first year we did it was 2021. And the reason I show that too is because these implementation plans take some of their guidance from the state of the climate supplement from the bulletin. So what we write there has a further impact with regards to decrease. All right, here's the combined GO 16 and 17 GLM flash density for 2022 relative to the 2019 to 2021 mean. And what key things happened then, where we had the triple dip 3-year La Nina, which ended in March. Then we shifted into an El Nino, and now COVID-19 with reduced industrial emissions. And one of the big scientific questions is, what exactly is the relationship between aerosols and lightning? And it's very, very complicated. And so we're still trying to unravel that. But initially, the dip we saw was observed here by the lightning imaging sensor on the space station. If you look here at 2019 to 2021, this dip that I'm highlighting with my cursor, people were jumping on board and said, oh, that must be due to the reduced emissions. And you see it in the US and you see it globally. But then people started to learn, wait, there was this triple dip La Nina. Well, what happens with La Nina and El Nino? The large scale circulation and Rossby waves also are altered. You can see there's really no decadal change over this 20-year history. And there's some interesting papers by Michael Fritsch from Penn State some years ago, where he looked at what's the impact on mesoscale convective systems with regards to El Nino and La Nina. And that's important because they shift the weather pattern. So not each El Nino or La Nina is identical because you're getting shifting patterns, but you'll see that the enhancement of rain and precip, and now we're looking at thunderstorms related to extreme weather are also impacted. So I got this cartoon here from NOAA, the NOAA climate program, and here's a summary of El Nino wintertime impacts. That's when the effect is seen the most significantly. And what I wanted to focus your attention on is within the field of view of GLM, along the Gulf Coast, what happens is you get a split in the southerly jet. And what I'll show you another figure here on what we observed during the 97, 98 El Nino. And notice Southeast Brazil as well, you get a wet period. And then we'll look at the anomalies for 2023. But first, let me take you back to the first paper that I did with the 97, 98 El Nino. Some of you may be old timers. I had noticed watching the radar on TV that there was storm after storm going through the Gulf and Southeast US, just like we're observing this year. And I happened to talk to Chet Ropolevsky and Mike Halpern in the climate office. I said, what's going on with this? And they had just written some of their seminal papers on El Nino. And so I got on board with that to see what was going on. I was able to get a hold of some of the Vizsla lightning data, and we had just launched the TRIM lightning sensor. And what I want to point out here for that last strong El Nino was the Gulf of Mexico had 200% more hours with thunder and days with lightning, as in the La Nina year. If you see here, DJF December, January, February 98, 99 below, and El Nino above. The other big change, if you look in the South China Sea, over here, a big enhancement during El Nino, and what happened, there was about a 180-degree shift in the atmospheric circulation. So instead of cold air going over the ocean or warm air going over the land, we had a shift in that, and that enhanced the thunderstorm activity. And then pointing to the Vizsla data here, notice 97, 98 here in the bottom left panel, compared to all the other years, a tremendous enhancement in thunderstorms. And then lastly, I have the wind anomaly. This is all in that paper, from the 68 to 96 average. And I don't know if you can make out, here's Florida down here, but we had a stronger southern branch of the jet. We had 16 cyclogenesis events in the Gulf of Mexico. A lot of these became nor'easters and went up the coast. So there was a dramatic shift, and it does affect the distribution of lightning. So now let's look at the 2023 thunder hour anomaly for El Nino. Of course, we can't go all the way through to the end of the year because the DJF part hadn't occurred yet. But a couple of things I want to point out here. We had about a 2-degree temperature increase in the sea surface temperature in the Eastern Pacific, which is not unusual for El Nino. I have the Woolen data, the Worldwide Lightning Network data, which is one of these ground-based, very low frequency global data sets, and GLM goes east, goes 16 here on the right. They both find the same maximum off of the Columbia coast. I have a white star here that indicates where that peak is. They're about the same place. The GLM has roughly 25% more lightning in the maximum grid, and recall that the Woolen network sees primarily cloud to ground lightning and not the in-cloud lightning, so a lot of that difference is due to GLM seeing in-cloud lightning. Other features to notice here are Southeast Brazil. That's a phenomenon that's also been documented in the literature with El Nino, with the increase. And then you see a lot of lightning in Western and Eastern Canada, and we know that a lot of the fires in Canada were started by lightning. Those are some of the major features that we see. And I also want to point out, look at Mexico now compared to that earlier figure, where we had during La Nina a strong or a lot of lightning in the Sierra Madre. Now it's been a negative anomaly. The last thing I want to touch on is what's going on in a warming Arctic. Here's some plots that are in our 2022 or 2021 report in BAMS. If you go look at those, if you look at 2010 to 2014 and looking at the Arctic, you don't see lightning up there, but in 2015 to 2020, we start to see more lightning, and we still see it in 2021. This is perhaps due to the diminishing sea ice in the Arctic, although we've not done a study. I don't know of a study that proves that for sure. It could also be impacted by fires in Asia at a very high latitude. And what I want you to also notice here is from Vizsla on the left, these are lightning events north of a given latitude, starting at 65 degrees north at the top, 70, 75, 80, and 85. And you notice this trend line starts peaking up when you get up to 80 degrees latitude. So it is in the high Arctic. We're seeing that. And then I want to, as a lead in to the lightning mapper on GeoXO, show you here, Alaska is around 150 degrees west, and we're starting here at 60, 65 north. This would be a region that we would be able to observe if the LMX on GeoXO has the greater coverage, which is what we're hoping for. And in part, I think it's really important because of the warming Arctic that we are able to see to higher latitudes. The EUMETSAT lightning imager, for example, can see up to 70 degrees latitude from Europe. So they also have increased coverage. And then here is the one of the predicted fields of view for the lightning mapper for goes east and goes west combined. You'll see that we get very good coverage with 8 kilometers spatial resolution or better. It could be much better, and we'll find out when the vendor is selected and it's announced what this instrument will look like. But we will have better performance up to higher latitudes and greater overall coverage. And then lastly, comment about thunder days. That will extend the climate record we have. There's a nice paper by Thomas Levine from Texas A&M Corpus Christi, where he compared thunder days with the lightning imaging sensor and was able to show how well you could take the thunder day record, which is recorded at weather stations around the world, back in time. And here is a map of thunder day records we're trying to collect and get digitized. And the Copernicus program in Europe has agreed to archive all these data. Some of these have been digitized, they're already there. Large parts of the world are not digitized, they're not there. Like, for example, Soviet Union, Russia, China, much of Africa. And so there's an effort where the WMO is helping us gather these records. So in summary, lightning is a global natural hazard. I hope I've convinced you of great significance. The LMX and evolution advancement over GLM and the MTG lightning imager. The LMX proposals are under evaluation. It will no doubt have higher spatial resolution. It'll have better temporal resolution, which will improve the detection efficiency, and also greater coverage, especially to higher latitudes and affecting Alaska, which is not well sampled or observed currently. And then this question about how lightning, the central climate variables, such as is associated with other variables, and you can see the list here, including ENSO, MJO, atmospheric composition, upper level humidity, and I think we've just launched Tempo, and that data is just becoming available. But the atmospheric composition instrument, looking at that along with the lightning mapper and GeoXO, I think will yield a number of discoveries and help us better understand how that's all connected. And then lastly, raising lightning safety awareness. We're trying to collaborate with the World Health Organization and the WMO Disaster Risk Reduction Natural Hazards Program as well. All right, that's all I have. Thank you. You want to take the screen back? That's fine.
Yeah, thank you, Dr. Stephen Goodman, for this insightful and relevant presentation. I think we can all relate to the lightning problem, especially if you're working at a WFO, and we're very excited about GLM, its uses, and also what is coming with GeoXO. So I will encourage attendees to stay for the question and answer section. Whether you are in a WFO or a regional headquarters, please stay. We're gonna make a few announcements now and then proceed to questions and answers section. So complete the Satellite Book Club presenter facilitator form that is being posted in the chat room as of now. So for next week, if you are interested, we will have on Thursday, March 14th at noon, same time, same place, Kyle Eskew from the University of Oklahoma. Kyle will be discussing long-range smoke transport using aerosol measurements. I think this is also a very relevant presentation, especially with the wildfires from last year coming from Canada to the east and central US. So also remember, if you're interested in presenting or facilitating a future Satellite Book Club presentation, you can contact Emily Maddox or Kashat Bowman. Also, if you wanna, at your weather forecast office, you wanna have a new satellite product or questions about Tower RPM, you can contact the Tower S team. And well, we will go into questions and answering now. So I will kind of like break the ice for you guys. So Dr. Stephen Goodman, you were talking about the new LMX and the GeoXO. So I do have a question because when I think about this new instrument, it needs to bring something new to the table. So I was thinking first to, about spatial resolution, kind of like bringing GLM to trim resolution, spatial and temporal resolution. But I also thought about detection efficiency. I know during daytime, the detection efficiency normally decreases. It goes from 90 at night to 70 during the day. Is there any improvement in detection efficiency with the new GeoXO instrument?
Yes, good question. And we think that we'll have better sensitivity and we'll also have smaller pixels. I can't say what they'll be because we don't know which vendor is chosen yet, but hopefully better, maybe even better than 8 kilometers at nadir. And so we'd be able to see smaller flashes and get more of the signal into a pixel. So we do expect better performance. And I think even at the higher latitudes, one of the issues with GLM is, for those familiar with the data, we have reduced detection in the Northwest US from either satellite. And part of that is due to spectral out of band response for the instrument. We have a very narrow 1 nanometer interference filter so that we just focus on the emission line that has the lightning in it. Well, it turns out that you get a spectral shift with view angle, and having it only 1 nanometer causes some of the signal to go out of band. And so hopefully the new lightning mapper will have a broader spectral band filter, in which case we'll be able to do better, perhaps much better, covering the Northwest US.
Okay, thank you so much for that. And I just want to remind us in this, if you want to ask a question through the chat or just, come in and open the mic and verbally ask your question. So I'm going to read some questions that we have had, Dr. Steven, from the chat. Dan Lindsay is asking, do you think the lower lightning frequency in East Pacific tropical cyclones relative to the Atlantic is due to cleaner air there, meaning fewer aerosol content?
Yeah, Dan asked a good question, and there has been some papers. Steve Businger from the University of Hawaii in particular was very interested in that problem. And we know the Atlantic air is a lot dirtier due to all the industrialization versus the Pacific. And he does have some evidence that the Pacific hurricanes and cyclones have less lightning than in the Atlantic. And that again raises this question about what is the role of aerosols, either as CCN or even in affecting, say, the updraft strength. There's some papers by Danny Rosenfeld, which some of you certainly know, where he argues that if you have aerosols, it'll cause the precipitation, instead of going up into the freezing level, to fall out. And then you don't get the mixed phase interaction of ice crystals and droplet pellets and hail in a rich medium of supercooled water, which we think is important for electrification. And that would be part of the explanation for why the more pristine Pacific would have less lightning. But obviously that's a very good question to pursue. Thanks, Dan.
I also want to add, I think it was a paper from Takahashi in 2003, 2005, I don't remember on, where they compared lightning intensity in a monsoon environment versus a continental environment. And one of the main, results was that, the aerosols content was a variable that they should take into account to explain this variability, of land versus a maritime environment.
Yeah, it makes sense. If we don't get raindrops to get up in the cloud and freeze, we're not going to get much in the way of electrification.
Right, yeah. We also have a question from Bill Soiver. He's asking, will parallax at higher latitudes be a concern?
Yeah, thanks, Bill. Parallax, as you know, is still an issue for us. The forecasters seem to have adjusted to that issue when using the data. We know that even in Alaska with the current GLM, they're able to see a little bit of lightning, at the southern part of Alaska, and they find it's still useful for cloud diagnostics. So while, yeah, it'd be great to be able to resolve parallax, you're kind of stuck when you're at the equator looking at a high view angle. But if you're just mapping the lightning to, say, the ABI to the imager, they both have the same perspective on clouds, and you need other information, I think, to properly adjust. And that's where the ground-based lightning networks are still very useful, because they don't suffer the parallax problem.
Okay, thanks. We also have another question from Travis. He says, great talk. And the question is, with the warming climate, have you noticed any changes in the frequency of lightning by season, especially average around the world?
Yeah, I don't know that that's something that I have a good grip on, or that we've looked at. With the warming climate, the biggest focus has been on high latitudes where changes are happening very quickly. It could be that when you're looking more in the tropics and near extratropics, that kind of thunderstorm activity is a lot controlled by the topography, being over land, the coast, the mountains. And that signal may, I'm just speculating, may be very small, say, compared to the one we're seeing at high latitudes. But someone will write a paper, find a grad student who wants to look at that.
Thank you for the question and the answer. Dr. Steven, I also have a question regarding lightning discrimination, because I do remember reading some papers from, I think his name is William Koshak from NASA. I don't know if you know him, but he was working in, right, he was working in lightning discrimination, like some algorithm to say this percentage of the lightning detected by a satellite, whether it is LEO or GEO, will be cloud to ground or intra-cloud or cloud to cloud. Is there something new regarding that algorithm, or something that will improve or
Yes.
actually?
So, oh, sorry, did someone want to answer that? Okay, what I would say on that is what Bill found was if he looked at a bulk data set, I think it was like 500 or 1,000 flashes, he could say with some confidence what fraction were in cloud and cloud to ground. But beyond that, more recently, Jacqueline Ringhausen, who's at the Severe Storms Lab and the Cooperative Institute in Oklahoma at OU, did a machine learning study for her PhD with Phil Bitzer at the Alabama Huntsville. What she found with 20 predictors and a random forest methodology was that she had, I think, over 75% accuracy in declaring an individual lightning flash as in cloud or cloud to ground. And that would be huge, because then for public safety and fire ignition, we could say with GLM the likelihood of being an in cloud or cloud to ground strike. And even beyond that, I had discussions with the folks at the Global Systems Lab, and said, if we could come up with something, you guys might be able to forecast not only the probability of lightning, say out to 24 hours, but the characteristic of the lightning. So the likelihood, say, for a cloud to ground lightning maybe affecting fire emission, which I know a lot of NOAA is interested in. So I think there's a lot of opportunity going forward, and how LMX will help with that is the smaller pixels will make that detection much better, and then also looking at continuing current, which is the duration of the lightning discharge in contact with the fuel at the surface, all the decayed and dead vegetation. And I think obviously having better resolution will certainly help us in that regard for fire applications.
Sounds good. Thank you so much. We also have a last minute question from Michael. He says, your presentation, Steve, you are the space-based lightning monitoring master. On your slide showing the timeline of the lightning rates with TRIM and then the International Space Station LEAS, you hinted the lower rates on the more recent ISS LEAS part might be attributed to lower industrial activity during COVID. But are there any significant differences between the TRIM and the International Space Station lighting instruments that could explain the rate differences?
Yeah, thank you, Jammer. So the lightning imaging sensor on the space station was a flight spare, excuse me, for the lightning imager on trim. And even before that, we had an engineering prototype that we flight qualified. We call that the optical transient detector. They're all the same instrument. The big difference between the ISS and the trim instrument is blockage by the space station itself. And there's some reprocessing studies just getting started for the end of mission, which called phase F for the space station lightning imager. And they are finding that the detection is reduced by a few percent, but it's not enough to explain the big difference we're seeing. And again, points back to aerosols. And the question is, what is their impact? I think it's a great question to pursue, this role between aerosols and lightning. I know it's been looked at in the past, but I think now with the space-based observations, we have an unprecedented opportunity to better understand it.
Okay, thank you. So we're gonna wrap up now. If you have more questions, you got submitted to Tavares or Dr. Stephen Goodman. Jordan, we're going back with you.
All right, thanks so much, Steve, and thank you so much, Adrian, and thank you everybody for contributing to the discussion. As a reminder, the Satellite Book Club continues next week, Thursday, March 14th at our normal time, 12 noon Eastern Time. Kyle Skew is going to be talking about smoke transport using aerosol measurements. In the meantime, if you have any questions for the Tavares team, you see them all here. Hello, everybody. Please feel free to get in touch with us, either directly contacting Kashad and Emily by email or by using the NWS internal Slack workspace, hashtag TowerS. With that, we'll wrap it up for today. Once again, thanks everybody, and happy meteorological spring.